Probabilistic linking, Cody Custis, Zero Consulting. So our learning objectives. Here are the learning objectives, the key takeaways. I'm trying not to get too heavy into the math and specialized terminology. Mostly, I want to talk about this as an example of joining and see how well a project can work. So we have the cross join, the three categories: automatic match, manual review, not a match, and finally the outcomes. Did it work? A cross join, aka Cartesian product, takes all the elements of one set and combines those with the elements of another set. Example: weekdays: Monday, Tuesday, Wednesday, Thursday, Friday, 5 elements. Working hours: 8 o'clock, 9 o'clock, 10 o'clock, 8 elements. Maybe you skip lunch in there. And cross join. So Monday 8 o'clock, Monday 9 o'clock, all the way up through Friday at 4 o'clock, 40 elements. So it's taking the elements of one set and multiplying them by the elements of another set. The example we'll walk through today is using probabilistic linking to join birth certificates to death certificates. The inspiration for this was a project at the state of Montana where birth certificates were marked as deceased if an individual had died. There were a few conditions. We only looked at people who died in Montana who were born, or claimed to have been born, in Montana. That limited us to only being able to match about half of all death certificates. Also, we limit analysis to fields that have been present on Montana birth certificates for a long time. Most descendants would have been born in the 1920s and 30s, and our electronic databases go that far back, just in terms of keeping the files. Also, this project was done a long time ago. We manually implemented most of the programming using SAS. The theory behind automatic join programs such as linking is similar. One of the reasons that matching birth and death certificates is challenging is that, based on manual review, things change. Individuals that are clearly the same person based on a manual review, but the date of birth may be off by a day or a year. Likewise, many people, often females, choose to change their names between birth and death at marriage. This tradition makes it difficult to use basic linking. So you see that manual process where we're manually reviewing things, and we want an automatic process to get our potential matches. We've got one example of Wayne here, a very simple model. If the full name matches, we'll give somebody 100 points for a potential link. If the date of birth matches exactly, 10 points. And maybe as a tiebreaker, if the mother's full name matches, 1 point. We look at a pair of variables, one for birth certificate and one for death certificate, and see if those match. If they do, we assign a value of 1, otherwise 0. For example, if birth first name equals Clark and death first name equals Clark, we assign a value of 1. So we're trying to figure out what variables match between potential matches. Little bit about data cleaning here. For data cleaning, one might use a SoundX algorithm to handle similar names and spellings. In practice, we found that merely taking substrings of names, such as the first 4 letters, worked as well for practical application. For dates, we wanted separate day, month, and year. Based on that prior experience, day and year were most commonly shifted by 1. So you'd have day shifted by 1 or 365. Indices are a way of organizing data for joining. SQL, both SAS and non-SAS, allows users to create an index on a variable. Adding an index to date variables drastically speeds the join process. There is extensive literature about the best kinds of indices and more advanced versions, including the hash join. We'll just mention that indices exist. We also assign weights to each pair of matching variables. Those weights might be based on a subject matter expert's opinion. Matching last name would usually count for more than matching county of birth. Alternatively, weights can come from a data set that is known to match based on manual review. Thirdly, it is possible to estimate weights based on a subset of the data. That's beyond the scope of this discussion. There is some theory that a weight should vary based on how common a variable is within a data set. For example, Theodore, number 1 in 2022 Social Security baby names, would count for more than Chosen, 835th and storming up the ranks. In practice, we found that to be unnecessarily difficult to compute and offer little benefit. Also, a weight has to be finite to be used as part of a probabilistic match, otherwise it's a blocking variable. That means the probability of matching can't be 1 for true matches or 0 for true non-matches. This slide, above all, is the key to the process. We assign all pairs of matches to 3 categories. If the odds of being a match are high, we declare it a match automatically. If the odds are in the middle, we do manual review. If the odds are low, we declare it not a match. How to set those odds depends on the goal of a linking project and the resources available. Let's reiterate that. Once again, this is the key takeaway from the presentation. A process that breaks things down and creates far less manual review is a good process. If we just cross-join these 2 data sets, 4K death records times 500,000 birth records, that equals 2 billion. There are way too many pairs to consider. This is where blocking variables come into play. A blocking variable is a variable that limits join options. Blocking variables are used to simplify computation. We might consider using date of birth. From prior experience, there are roughly 30 records for each date of birth in the death file. It actually varies by decade and birth rate. For last name, Social Security records show that Smith is the most common at roughly 2.5 million in the United States. Let us just use 1% as our potential estimate of potential last name matches. Once again, common last names vary by decade and locality. If we were to use a substring or soundex on that variable, the number of potential matches would greatly increase. So we see that looking at date of birth, now we only have 120,000 to compare. Last name, 20 million, but that's an upper bound. And computers can compare 20 million easier than they can 2 billion. We can do multiple passes using different blocking variables. Even if a true match isn't found in the date of birth pass, that could be found using a last name pass. Eliminating matched births in a first pass leaves many fewer records to match using a large space of potential matches. There are other potential variables we could link. Based on manual review, it was common for an individual's last name at birth to become a middle name at death, especially among females. For example, Marge Bouvier becomes Marge Bouvier Simpson. So let's look at the output. How well did this work? From our death certificates file, we were able to match roughly 95% with high enough probability to declare them automatic matches. And we did this by doing a manual review of a subset of records. Roughly 3% from there would have required manual review, some of which were a true match, some of which were false positives. And finally, 2% had matches that were obviously false. Low probability from our algorithm, and manual review said they weren't there. So in the end, what happened with this project? Well, due to decisions made by managers, we didn't implement the algorithm for Montana records. However, based on the large amount of resources needed to match, we did implement the algorithm for a data set of individuals who died in California who were born in Montana. That was about 4,000 individuals, with multiple years of data from California. That saved roughly half a year's worth of full-time work. That's what I'm saying about the resources. Finally, we implemented a similar algorithm to match Montana death certificates to highway patrol data. Although the programming resources weren't burdensome, the proportion of matched records was lower due to the nature of the fields included on highway patrol data. And thank you for your time.